Hello everyone, I'm pleased to attend this conference. My name is Yanfang from Xi'an University. The title of my presentation is Critical Compressive String of Grease-Welded Pipelines with Misalignments. Thank you. Now I'd like to present my report, which is organized into 6 sections: introduction, numerical modeling, parametric studies, compression of critical compressive string models, modification of CSC models, and conclusions. The first part is the introduction. Oil and gas pipelines are often subjected to additional loss induced by soil pipeline interactions when crossing adverse geological zones. This loss can lead to displacement and deformation, thereby compromising the service safety of the pipelines. When cracks, corrosion, dents, or other defects exist in the pipeline or weldments, such additional loss may cause the pipeline to denting or rinking, which in turn can result in pipeline breaks. Oil and gas leakage may occur, potentially triggering fires or explosions that threaten human life and property. Grease welding is a common technique used for drawing pipeline segments. However, various misalignment types often occur at the grease weldment, such as offset misalignment, equal diameter misalignment, equal thickness misalignment, and overlapping misalignment. These imperfections make the grease weld become weak region, where fracture or buckling is more likely to initiate. However, most previous studies focused on local fracture and string concentration, while the influence of misalignment on the buckling behavior of grease-welded pipelines and combined loading remains insufficiently understood. To evaluate buckling behavior of pipelines, researchers have conducted a series of experimental and numerical studies. A CSC model is proposed to account for the effects of geometric fractures, loading conditions, and material properties. Existing CSC models such as CSA-DNV, Dory model, and CIS model. Therefore, current research lacks applicability to pipelines with misalignment, highlighting the urgent need to a modification CSC prediction model that can accommodate variable misalignment types. The second part is numerical modeling. Shell elements are employed to model the pipeline, which is a final mesh is used at the weld location. Four misalignment types are considered. Type 1, offset misalignment. Type 2, unequal diameter misalignment. And type 3, unequal thickness misalignment. And type 4, overlapping misalignment. The loading and boundary conditions, a two-step procedure is adopted. Internal pressure is the first step and followed by a bending loss at both ends at the pipeline of the pipelines. And the model validation is then performed, showing that the simulated bending moment and the average curvature relationship closely matched by the work of soda. The deformation patterns and the buckling location are also in good agreement, confirming the accuracy of the mesh and the loading conditions used in the numerical models. The third section is the parametric studies. In this section, we investigate the effects of misalignment type, amplitude, and angles on buckling behavior of pipelines. The figure on the left shows a diagram of deformed shape. We calculate the compressive strain using the pipelines spanning one diameter of the grease weld region. The, the The results compressive strain and the average curvature curve is shown in the figure on the right. As shown in the figure, as loading procedures, compressive strain continuously increases until reaching critical point where the pipe beginning to buckle. As misalignment amplitude increases, the compressive strain and the curvature curves shift progressively to the left. The marked point in the figure indicates a critical point. The horizontal and vertical coordinates respected the critical bending curvature and the critical compressive strain. Then the critical bending curvature and the corresponding CSC are extracted to examine the effect of misalignment taps. It can be observed that tap 4 overlapping misalignment has the least impact on critical curvature and CSC. Tap 1 offset and tap 2 unequal diameter misalignment exhibit essentially identical effects these parameters. Type 3 unequal thickness misalignment exerts the great influence, leading to the greatest reduction in these parameters. The presence of welding misalignment significantly reduces critical curvature and CSC. For the four misalignment types described above, type 2 and type 4. Type 2 and type 3 are uniform around the circumference. Type 1 and type 4 are uniform. Then it is necessary to consider the effect of misalignment type as misalignment angle. As shown in the figure on the right, for type 1 offset misalignment, when the loading condition remains fixed, the pipe can shift in different directions. And for the type 4 overlapping misalignment, three conditions can be considered. In type 4A, both pipe segments exhibit overlapping, and a certain angle change occurs between the major axes. In type 4B, both pipe segments exhibit overlapping, and the major axes are maintained at 90 degrees, while the loading direction varies. In type 4C, one pipe segment exhibits overlapping, but loading is applied in different directions. This slide presents the compressive strain and the average curvature curves for different misalignment angle and types. For type 1, type 4B, type 4C, as the angle increases, the curves generally shift to the right. Both the critical bending curvature and the CSC increase the angle increasing. But for the type 4A, the result is opposite. The first part presents a compression of critical strain capacity models. We compared the four prediction models with our simulation for four misalignment types. The results indicated that the CIS model generally consistent well with the type 1, and the Dory model significantly overestimates the numerical results, whereas the DNV model is close agreement for the cases without misalignment. And the CSA model is lower than the numerical results because it implicitly incorporates pipeline's imperfections. In the fifth section, a modified model is developed based on the CIS model to account for misalignment in grease-welded pipelines. For each misalignment type, the effects of misalignment amplitude and angle are independently fitted, achieving fitting accuracies exceeding 99% and 97%. This slide presents the final revised model. In corresponding FDP, FYT, and FG item, The FGI term contains four variables, where FDP and FYT term retain the CIS model. Accordingly, it is necessary to verify the applicability of the FDP and FYT terms for girth welded pipelines. So this so this slide shows the validation results. For diameter to thickness, as D to T increases, the compression, strain, and the average curvature curve shifts to the left. The error decreases from 8.3% to 3.5%. As the internal pressure increases, the curve shifts to the right. The modified model remains in close agreement with the numerical results. And as hardening exponent increases, the curve shifts to the left, and the consistency between the predictions and the numerical results remains excellent. In the finally section, the main conclusions. Firstly, the moment and the curvature curve decreases with the misalignment amplitude increasing, and equal thickness misalignment is the most dangerous. Secondly, structural stability is lost when the direction of maximum misalignment coincides with the bending. Thirdly, the results obtained from the CIS model are close to the critical compression strain calculations. Fourthly, the modified model of girth welded pipes containing misalignments incorporates the effects of four misalignment types, amplitude, and angle. This concludes my presentation. Thank you very much for your attention.